Good day. Good afternoon. Thank you so much, Provost, Ivalo, Lloyd Griffith, Stanley Schiffer for the introduction, and Dean Paniotis, who's here, and all other senior members who I've not had the opportunity to meet, and distinguished friends and colleagues and students. So it's a great opportunity for me to come here, and I want to thank you at the outset for being able to find some time from your busy schedules. I know how hard it is to actually find some time from your teaching or your other work commitments and to make it to such a presentation. And I think it's very important that your participation has to be highlighted here. And that's what really makes this event really successful. So I want to thank you all at the outset, and I'm very honored to be here. And I thank the review panel, Linda and Assistant Provost Holger, for processing this event and organizing it till this date. Geospatial technologies are something which is very important in US these days. Along with nanotechnology and biotechnology, these are the technologies which are going to define the next 20 or 25 years. There's going to be a tremendous career growth in geospatial technologies. In a few minutes from now, I'll explain what geospatial technologies actually consist of. But I'd certainly like to tell you that they include three important technologies, some of which you may be familiar with already, because you drive a car and you see a GPS and you see a street map, which kind of tells you where you're located at a certain point in time. So there are three important technologies which are given a new word, geospatial technology. One of them is Geographic Information Systems, which is also known popularly as GIS. Then the other one is remote sensing, which I'm in a sense doing it because I'm interacting with all of you without touching you. That's what it actually means, remote sensing. And the third one is Global Positioning Systems, which means GPS in short, the technology which you use in your cars, which is facilitated by a constellation of satellites which are always in the space and which rotate the Earth twice in a day, and which gives us signals which we can use for locating different features. So I'll be talking a little more about those, but I thought it's very important to mention what geospatial technologies are in the beginning. Today's lecture, I'm going to walk you through these three important technologies and also discuss a project which I did over New York City, which means all the 5 boroughs, by looking at multispectral satellite images. In short, multispectral satellite images enable us to study the Earth from time to time, which means I can map New York way back in 2000, and I also can map New York now in 2011, which gives me a tremendous amount of information about the Earth in terms of, for example, how much urban sprawl or how much a particular city has grown, and why has it grown in that certain fashion. Has it grown alongside a river? Has it grown alongside a corridor? Has it grown alongside a highway? So all these things could be studied by using remote sensing data for a given period of time. So let me begin the talk. This is the title of my talk here. It says Mapping and Managing the Earth from Space. I made it very general, but you'll understand why I use this terminology here, because you can literally use this technology in any science fields. Any activity which involves location-based analysis can use these technologies, which means it's not restrictive only to science. Even a historian can use remote sensing data or GIS. So it kind of reaches out to almost more than 90% of the activities which have a spatial component, or which have a component which has a location on the Earth's surface. And this study is about mapping features from satellite images. When I say features, I mean it could be tree cover, it could be roof types, it could be the street network, it could be water bodies. So you can literally map all these features from the Earth's surface by using remote sensing data. Different people, different sciences have different focuses. They might need this information in different capacities. For example, an environmental scientist might want to know what is the tree cover over New York City in 2000 as against today. What has happened to the tree cover? Has it dwindled in time? What are the reasons for it? From an urban planning perspective, a person might want to know which particular borough has more streets than it had a few months ago. So all these possibilities enhance the value of geospatial technologies. So once again, geospatial technologies include GIS, remote sensing, and GPS. I mean, Stan has already introduced me, but I've done most of my teaching in Australia. I've been in US since 3 years now, and what really brought me to US is a very personal reason. I got married. My wife is from New York, so I had to come here.
So before you came, you were doing remote sensing?
Yes. Yes. Remote sensing through the internet. So my specialization, I'm in the School of Geomatic Engineering. Is a very popular school in university in Australia. It's one of the best schools there, and they do a lot of studies. And their GPS programs is one of the best.
What does geomatic mean?
Geomatic actually means if you're looking at a satellite data, and if you want to extract accurate measurements, you have to use a lot of photogrammetry. You have to use stereoscopes. So the science of extracting measurements from satellite data, accurate measurements, is called geomatic engineering. For instance, if you wanted to make a street map of New York City as of last week, you can actually extract all that information from a satellite image. By developing automated algorithms, you can extract those linear features. So that science of extraction and making those measurements very accurate is called geomatic engineering. I know we are all engulfed by this tragedy over Japan, and I was in Sendai 5 months ago delivering a talk at the 6th International Remote Sensing Conference. So it really makes me very sad because some of the places where I actually walked are so devastated. And I was looking at CNN, some of the video clippings have been horrendous. And I want to show you NASA-generated data, which is taken on the 11th of March. This satellite, the sensor, the name of the sensor, the satellite is a platform. The name of the sensor on the satellite is called Landsat. America, US has been running Landsat program for over 30 years now. Of late, they have registered some technical problems. But the Landsat senses, it's a multispectral sensor, which means we sense only in the visible range. We sense from 400 to 700 nanometers. But a near-infrared sensor senses beyond 700 nanometers, up until 1100 nanometers. In other words, if we had a lens which can sense from 700 to 1100 nanometers on the electromagnetic spectrum, I can pretty much see your arteries and veins, which is why you see all these red areas here. I'm not sure if you can see the pointer. It's kind of very luminous.
Can we shed some of the lights?
Can I? Does that make it better? Or? Yes. If you see all these red portions here on the image, this is quite distinguishable. All of you probably can make out what this is. This is an airport. This is a Sendai Matsushima airport here. And all these red areas, they appear red because this particular Landsat sensor senses in the near-infrared wavelength, which means green trees or trees with a lot of chlorophyll content appear bright red. And this was taken on the 11th, obviously before the earthquake. And this, you can clearly see here, these are the built-up areas, and these are the agricultural areas and the trees. And this is the water body, which appears black on a remote sensing image because most of the light emitted by the sensor is absorbed by water bodies. So it appears black on the image. And these are very bright areas, which shows that it's probably concrete or built up. And this white to blue areas are all built up areas. And this is quite distinguishable by the shape. It is obviously a river. The same image after the disaster. So you can see all those vegetated areas are completely submerged underwater. And it's completely, all the vegetation has vanished. And please remember, this is a 30-meter resolution image, which means every object which is only 30 meters large can be detected by the sensor. So it's a very coarse resolution sensor. If you want to look into more details, you have to fly low or use an aerial photograph like Stan mentioned. But this one, the resolution is fixed, and these images are taken from space at a very high altitude. But these Landsat images, because it has a coarse resolution of 30 meters by 30 meters to a pixel, they are very good to map regional changes, to map changes over a large area. So remote sensing databases come in different resolutions. Some may be as high as 1 meter by 1 meter. For example, the data which I'm going to show you, which I've used in my study, has got two resolutions, 5 meter by 5 meter and 1 meter by 1 meter. And there are also, yes?
Are these taken from geosynchronous orbit?
Yes, they are taken from geosynchronous orbits. And there are some satellites which can read the logo on your shirt. But they're only used by the US Defense and not for civilian purposes. So what I'm trying to draw your attention to is the resolutions come in a wide range. And what resolution you choose for your study depends on what you're trying to study. But the advantage of using a satellite is basically it provides us with a synoptic view. Most of the times when we are walking on the Earth's surface, we don't get this view. You're not able to see that there are many factories juxtaposed to a water body. You're not able to see that a water body is very close to a residential area because you're walking in a two-dimension. But when you get a snapshot of where you live from above, your mental, the intuition changes. And you realize that in space, all these features are located either close by or at a certain distance. It is that very aspect that we exploit in geospatial analysis. So they are very synoptic, which means you can get synoptic information for this whole area from time to time. Since Landsat images have a very high repeativity, they keep on repeating the same place from time to time. The second advantage of using this satellite data is that you can get information in near real time, which means if you wanted to construct or make a street map of New York City as of last week, you can do that using satellite images. None of the paper maps which are sold in stores would give you that kind of currency. So we say near real time, almost real time. And of course, this is one of the most important factors where the advantages of using remotely sensed data is you can perform digital analysis. Each pixel on this satellite data, which is about 30 meters by 30 meters, can be processed in the computer. And each of those pixels has a certain digital number. For example, if it's a water body, it has an X number. If it's a tree, it has an X number. We call that the spectral digital number. We use that number to process the pixels in a computer and spew out maps. So that's the process which I've used in my study, which you'll have to, which I'll explain more in a few minutes from now. And of course, you can use this information in modeling and mapping. For instance, if there is a nuclear plant here, which can possibly spew out radioactive gases, which direction is the gas likely to go? So you can use a plume model, which has wind direction and other parameters, and it can actually go and tell you exactly which residential areas is it likely to engulf. So that kind of possibility is also there with this satellite data. It has the ability to integrate data from different sources. You could be a climatologist, you can put your information in here. You could be a historian, you could be concerned about some archaeological sites here. So you can get a snapshot of those areas. And you can work out how to actually study these different spatial features. And then, of course, you can make decision support systems. Like recently in Haiti, they wanted to find out which of those structures which are very vulnerable. So they used a series of satellite data. And they were able to map that information and provide it to Red Cross and a lot of other people. Because in situations like this, these areas are not accessible because of various reasons. So remote sensing data becomes indispensable in this situation. So I just wanted to tell you a few general things, but to be more specific, we have these three technologies, which together in US are popularly known as geospatial technologies. They include GIS, they include remote sensing, and global positioning systems. So what is a GIS? Basically, a geographic information system is actually a computer hardware, a software, data which is put into the GIS, and a person who runs it. Altogether, all these things are called a GIS. So basically what a GIS does is, suppose you wanted to find out how many people would be affected near a floodplain. You can do that analysis by mapping the number of buildings near the floodplain and also finding out how much is the rise in the floodplain. So once you have that information, you can turn that information back to a borough or a planning agency, and they can maybe draw a floodplain map. In fact, in most of US, most of the floodplain maps are drawn using a GIS system. So GIS allows us to view, it helps you to visualize, understand spatial patterns, question, interpret, and visualize data in many ways that reveal relationships. For example, in Sydney, I did a project with a professor from the Drug and Alcohol Research Center. He had a lot of information about people who were succumbing to drug overdose in New South Wales. New South Wales is the entire province. And he also had information about different injection centers in New South Wales. He wanted to find out what is the response time when a person is injected with a drug overdose. Can he actually make it to the injection center? The very purpose of the injection center was to treat such patients. So when they put all that historic data, millions of records and files, into the GIS, and they also put the existing injection centers, they found that there was a total mismatch. None of the patients would be in a position to reach those injection centers, just like fire stations. Fire stations are outgrown by urbanization. Fire stations are located historically, but they don't really serve the purpose if you can't make it to a certain disaster area within a certain response time. A GIS also helps us to answer questions and solve problems by looking at our data in a way that it is quickly understood and easily shared. If I simply ask you in the Queens area, how many women are there between the age of 40 and 55? You possibly cannot tell me off the top of your head. But with the GIS, you can literally map those population. And if I ask you some further questions, how tall are those women? Are they between 5 and 5 feet 6 inches? Map those population to me. And if I ask you about ethnic background of those people, so you can ask any number of questions. Once the data is fed into a GIS system, it can actually generate maps for you at will. So that's how a GIS works. We have different layers in a GIS. One layer could be a street network. Another layer could be building footprints. Another layer could be the number of trees in that area. Another layer could be land uses. All these layers are combined. And why are they talking to each other? Because they're all using the same reference location point. That is the strength of a GIS. Just like each one of you are sitting in this lecture, each one of you have an X and Y coordinate about you, which is unique to yourself. In the same way, all features on the Earth's surface have an X and Y location. So we use that power of location and do the multiple analysis. So in this case, this particular street aligns with this building. And this building aligns with this tree here because they're all in the same reference location. So that's how all these layers are tied together. That's the strength of a GIS. Remote sensing, I did mention in the beginning. It's basically a technique by which you look at a process or a phenomena without touching it. Suppose you wanted to study the Amazon rainforest. One option would be to send a team of people to Amazon rainforest, which is not going to be cost effective. And the information which they collect will never be consistent simply because many different people are involved. So if you use a seamless surface like a satellite data, you don't have to go there, yet you can get more biophysical variables of the tree cover or the canopy or the tree height or the diameter by using satellite images. And there are different satellite images specifically designed for different purposes. If you're interested to study the chlorophyll content in trees, there is a specific sensor which actually generates information about the chlorophyll content. If you want to understand the canopy diameter, there is a specific satellite sensor which does that for you. In some cases, a hyperspectral satellite data can do it all for you. So it's defined as a technique of obtaining information because it does not tamper with the sample. It's a very highly valued approach to studying the environment because you're not damaging, you're not destroying the samples. No, you're right. Traditionally, the energy collected. So the way it works in remote sensing data is every object has got a spectral and a molecular structure. So the signals are sent from the satellite and it hits a target. The target could be a water body. The moment the energy hits the water body, it absorbs all the energy. It doesn't reflect back. In remote sensing, we scientists, we work with reflected energy, the energy which manages to get back to the sensor. And there are many detectors and codes which actually collect the energy from the target. And those detectors are aligned to specific wavelengths in the electromagnetic spectrum. Some detectors work in the visible range. Some detectors work in the near infrared range, which is why you see those trees as red colored. So we are concerned with reflected energy. Since water does not reflect any energy, it appears black. So that's the science behind remote sensing. We call that spectral footprints. So a tree has a spectral footprint which is different to a bright object. A bright object has a spectral footprint which is different to a water body. Sometimes these spectral signatures are all mixed up. So that's where we spend most of our time. We try to map a pixel. And a pixel on the Earth's surface will have different features: tree, water bodies, and so on, all mixed up. So traditionally, energy collected and measured in remote sensing has been electromagnetic radiation, including visible light, thermal, infrared. This thermal data is also very useful in mapping urban heat island. So thermal data means they have thermal sensors which record heat energy. So in the night, urban areas, they release heat back into the atmosphere. And those signals are taken by the thermal sensor. So you know in US which are the places where the urban heat island effect is more. Obviously those cities where there is too much of construction and they're all clustered together. I'm just going to skip this quickly. So basically that's a satellite for you. And here you have those detectors. And each of these detectors here, they are designed to function and take signals from different wavelengths. Sometimes you might have a detector here which only senses in the visible range. Another detector here, it senses in the near infrared. Another detector senses in the middle infrared. So when a signal is taken and transmitted down to a ground station, you get a collection of visible energy, near infrared and middle infrared. Then it's for the scientist, once he gets the magnetic tapes, to actually uncover the truth behind those signals. And these are small examples of different types of satellites. Today we have different types of satellites which are used for weather purposes, which are used exclusively for mapping, which are used exclusively to study the phenology of vegetation, how vegetation changes from one season to the other. And the third part of the technology is GPS, which is Global Positioning System. So there is a constellation of 24 satellites in the space, which was originally launched by the US Department of Defense. Initially, they did not want to make it available to the civilians, so they encrypted the codes, which means you won't get the exact location. But later on, when they found that other countries are also developing the same technology, they actually released the encryption codes and made it available to everyone. So these GPS signals are used basically to locate the exact location of a particular object feature. So the way they work is satellites circle the Earth twice a day in a very precise orbit and transmit signal information to the Earth. Then the GPS receivers, they get those signals. And based on the time taken from the time the signal is sent from the satellite till it's received, the location is calculated by a method of triangulation. So the fourth point is used to confirm the location of a specific area and a feature. So that's how it works, the GPS. That's the constellation of satellites. These three technologies are cutting-edge technologies, and many job opportunities are supposed to be available for a lot of youngsters, graduates, in the next few years from now. So what's the relationship between GIS, remote sensing, and GPS? GIS, you can use any type of data. Let's say you had a historical map, which is in a hard copy format, which is with a museum, and the museum is very particular about preserving it. One way of preserving that map is by taking the map from the museum, laying it out on an A0 digitizing table. So you actually pin the map on a digitizing table, and you use a small, we call that a mouse with a crosshair line, and you trace all the features on the map. So the map gets converted from an analog to a digital form. So you store it in the computer. You make it as accurate as you can, and you increase the lifetime of that map. So that's one way you can actually do spatial analysis. So literally any data which is accurate can be fed into a GIS, and you can do spatial analysis. Spatial analysis could simply mean answering questions like, how many people would be affected in case there was a flood here? How many of those people live in single-family homes? How many of those people have an income between $60,000 and $55,000 a year? So the number of questions can be as many as you like. Once you feed the information and the data, depending on which perspective you're coming from, you can use that information for spatial analysis. We say spatial because it's always reference to a certain location on the Earth's surface. And remote sensing, how it is compatible to GIS is because we collect information using satellite data. We are in a situation in the world right now that there are more than 100 satellite programs launched by different countries. So there's a huge volume of data. And we are running short of people to analyze those. And yet, we have that, we get very perky when we see a new satellite program, knowing that there is so much of information yet to be analyzed. So that's where the field is at the moment. But there is certainly an ever-growing demand for people who can actually work with such data and take out features and extract features. NASA is very interested in extracting features from a series of images taken over the past 20 years so that they can map the changes and they can plan for the future. And GPS is always used in fieldwork and sampling. So if you want to collect sampling and fieldwork data, you have to be armed with a GPS so that you know exactly where your samples were. You can get the XY coordinates. And then you upload those details onto a map. So basically, this is pretty much the last slide before I discuss my, the project very quickly. So scientific investigation demands survey and field-based studies, all scientific investigation, which are expensive and issues with data consistency, like I mentioned before. Yes, please.
Yeah, when you were speaking of GIS, you showed us pictures, you spoke of a 30-meter or 5-meter or 10-meter resolution, and related those back to a computer piece of data over there. When you're speaking of GPS, is there a similar concept of resolution? Like if I'm looking at the one in my automobile, I'm probably, say, within a block. But if I'm doing an archaeological dig, and the whole dig is only 30 meters, and 30 square meters, are there variations of GPS so that I can get down to?
Oh, yeah, thank you very much. That's a very good question. We do have different resolutions. For example, I have a GPS at home, which is about $11,000. Now, the one which you use in your car has got a very lower precision. You have a very valid point. Suppose you want to map something in a sub-meter or a sub-centimeter accuracy, then the make of the GPS also helps you there.
And that's accessible by civilian researchers?
Yes, yes.
There is, down to
yes.
millimeters.
Yeah, there is a company called Garmin, G-A-R-M-I-N, who manufactures all types of GPS. There's another company called Navstar, who manufactures a handheld GPS. So you pretty much hold the system in your hand, and you switch it on, holding it for 30 seconds. And after a few minutes, just like your mobile phone, you get those towers.
So if you're doing an archaeological dig and you've got your grid over your site, you're using that kind of device to actually locate each item being found.
Exactly. And if your archaeological grid is rectangular in shape, you can literally take the GPS and walk along the borders. And when you come back to your office, you can actually upload the grid to a sub-centimeter level accuracy. But you do have some GPSs which really throws off the accuracy. But you wouldn't want to use those for scientific purposes. So for managing resources, demands information on changes over space and time. So geospatial technology is a useful resource for managing resources. Multidisciplinary study, just like I mentioned, it cross-cuts different disciplines, simply because most of the activities are connected with locations on the Earth's surface. So whether you're a historian, whether you're a social scientist, whether you're a natural scientist, you can all use geospatial technologies. So we need spatial information for planning, managing the urban environment. You could be studying climate change, urban heat island, urban sprawl, managing the natural environment, mapping floods, tree covers, parks, or climate change modeling. I just mentioned a few here. This list can be very exhaustive. So quickly getting back to my study, the main purpose of my study was to collaborate with a company called GeoEye. They are one of the largest satellite providers in the world. They're based out of Colorado, and they launch satellites every 5 years. So they're also listed on NASDAQ, and one of the satellites is called Iconos. Iconos has got 2 different types of spatial resolutions, 1 meter by 1 meter, one sensor, and then the other sensor is 5 meters by 5 meters. That's the spatial resolution. But they also have spectral resolution, ranging from the panchromatic to multispectral. It sounds pretty technical, but I just mentioned in the beginning that we all sense in the visible range. Like that, there are different ranges in the wavelength. So when I say multispectral, it senses in the visible as well as the near infrared. So we call it multispectral. It goes from one spectra to the other. So the purpose of that project was to map all the different types of features. When I say features, the tree cover, the building types, whether it's a gray roof or a white roof, the water bodies. Literally, whatever you see on the satellite, we were trying to map them. And how are we trying to map them? By doing digital image analysis of each pixel and using specialized computerized softwares.
Question.
Yes.
You said each pixel, so your satellite, you said that the scientists work with the reflected energy reflected signal.
Yes.
So you pinpoint a signal to that grid, to that square or coordinate, and then sense it back? Is that how it works? Or?
Yes, the satellite image is a surface which has got pixels. All the pixels are geometrically similar, but the objects which are on the pixel may not be the same. So when you're looking at a collection of pixels, one pixel represents maybe a collection of trees and buildings. Another pixel on the Earth's surface, because these pixels are all actually locations on the Earth's surface. So one pixel might have just trees. So the signal which you get from that pixel will be a collection of trees. But in an urban area, you might get trees and houses and paved areas, unpaved areas.
My question is, when you send the signal to each pixel from the satellite, so the reflected energy, I mean, so your satellite senses each pixel's reflected energy.
Yes.
Is that why the resolution is so?
Exactly.
Oh,
Yeah.
okay.
So basically, the reflected energy is collected by the detector cords on the satellite. And depending on which wavelength it senses, it captures those signals. And then those signals are transmitted to a ground receiving station. And we receive that data in magnetic tapes, which looks very fuzzy in the beginning. So you have to process the images for removing noise. By noise, we mean dust particles, which interfere the signal and the final image. So we process the image until we get some clarity that we can work those images with. Yes?
Sorry, I don't want
No, you're right.
to interrupt too much, but the light that, or sorry, the energy that's reflected is mostly light that's coming from the sun, or is it coming from the satellite?
That's a very good question. Actually, there are two types of satellites. One is called an active sensor. The other one is called a passive sensor. So just now, the professor, he mentioned, that's an example of a passive sensor, which means
which takes the
solar energy. The solar energy.
And the ones you're talking about mostly are these passive sensors.
The passive sensors, yes.
Okay, and the second question I got is, following up on his really, so each pixel has some kind of address, so you know where it's located.
Yes.
But also, it's got to have some kind of datum associated with it, right?
Yes.
And that, if this is multispectral, that must be a big, long pile of numbers.
Yes,
right?
yes.
Okay.
Yeah.
I got you. So it's basically you've got a spectrum for each location.
Exactly, exactly. The entire image is georeferenced. So as you move along from one pixel to the other, your coordinate, your reference point also shifts, depending on which point on the Earth's surface you're talking about.
I bet there's a lot more lists, numbers in the spectral information than
Yes.
there are for the two coordinates of the position.
That's
so
right.
The vast majority of the data you're moving around must be these spectra.
That's right, yeah. And when we talk about the active sensors are those sensors which are used all along the equator. Because these passive sensors won't work on the equator simply because it's overcast, because of the convectional currents and the rainfall and the weather. You know, if you go to countries like Singapore and countries which are closer to the equator, you cannot use a normal passive sensor because there's no sunlight which can penetrate through the clouds. In those instances, you use microwave remote sensing. So you use an active or a radar sensor. So radar, the difference between radar and passive is that the radar transmits its own energy. And it has the ability to penetrate through the cloud cover as well as the subsurface on the soil. So sometimes you use radar for studying soil, the topsoil also. So in countries where you cannot use passive remote sensing, you use active remote sensing. So it sends its own energy and its own illumination. So it hits the target, illuminates it, and then the echo from the target. In radar, we call it echo. The echo from the target goes back and forms different images on the sensor, which is transmitted back to us. So the project was to extract the objective was to extract specific target object features, just like I gave you some examples, over New York City, covering all the 5 boroughs, from very high resolution. We call them very high resolution because the spatial resolution ranges from 5 meter by 5 meter to a certain pixel and 1 meter by 1 meter. So you can literally see all objects which are 1 meter in size. And to develop, the second objective was to develop automated algorithms. When I say extract certain features from the Earth's surface, it's not an automatic process. You have to process the image, you have to classify the image, and then you have to check whether your results are accurate on the ground. After that, you get an accurate map. So I can generate a map which shows all the tree covers over New York City. And if I can do that for 2000 to 2010, that's a whole lot of information which many people can use. And all you need to do is to work hard and get that algorithm right, and you can simply test the same algorithm on the series of images. And you get the same, almost same results sometimes. So to assess the accuracy, without which you can never say that you've completed a project, and to develop spatial decision support systems, which can be used by a whole range of agencies and research networks. So that's the overriding objective. And this is the study area which we chose. This actually, I had to show this because this study is also appeared in a peer-reviewed journal, which I have the link for. And this is showing a part of New York City here. And this is the approach we had. We acquired cloud-free, orthorectified ICONOS very high-resolution satellite data from 2000 to 2010. When I say orthorectified, sometimes there are some distortions on the surface. All those distortions are corrected by using a planimetric scale, across the entire image, which means at any point in time you want to take measurements, you will get very accurate measurements. So that ortho-rectification is a very important process before you use any very high resolution data. And there are softwares which can do that, and students can learn them by just doing simple exercises, supervised, of course. Then we classify the image. We have two approaches in this study. One is supervised classification by looking at every pixel, and then the other one is object-based classification. I'll explain more about this as we go on. And after we classified with these two methods, we assess the accuracy of either two methods here. And finally, we get a GIS data, integrate it with these classified results, and we use it for different purposes, and modeling, and so many other different applications. So that's the Iconos image. I said it's a multispectral data. So you can see this is a true color. In the beginning, when I showed you an image over Japan, all the trees were appearing red. So that's what you can do with a multispectral. You can play around with the different channels, and you can switch them one over the other. So if you want to see them in a near infrared band, it appears red. But here, I've formed a true color. A true color image is quite similar to what you would see if you were to use a helicopter over New York City. So you would obviously see green as green. So that's a true color image. And you can see there are many trees out here. So this is the original image without any classification. The Iconos is a time series of satellite data. They're very expensive. So the entire project costed about $200,000 to $250,000. Because each image is sold on a square foot basis. So it's a commercial company. They charge probably $20 to $25 for every square foot. Award, this is from an award by the GeoEye Foundation. I applied for this award and I got the images. It took me about 6 months to get it eventually. So you have to work ahead of time to plan all these things. And then, like I said, the resolution is 5 meter by 5 meter in the multispectral band, which is MSS band, and 1 meter by 1 meter in the panchromatic band. So all these bands are simply different areas on a wavelength in simple language. And you have four, in the Iconos image, you have 4 multispectral bands and 1 panchromatic band. So the advantage is that you can map changes using multispectral, and if you want to have more details about any specific feature, you can use the panchromatic band, which is a grayscale band. So this is basically the fieldwork, sampling, design techniques. So before we start a project, we have to make sure the area where we are studying. We have to have a very good connection with the area which we are trying to sense using satellite data. So we literally have to go down on the ground and do some kind of a reconnaissance survey. Because eventually, you're going to compare the pixels you've classified with the real area. So it's very important to go down on the field and to do some random sampling and to collect some samples from the field. So we did that using both primary and secondary data sources. We did that using a GeoXH Trimble Pro XR GPS handheld receiver. This is a very powerful GPS, just to answer a question a few minutes ago. It gives me sub-centimeter pixel accuracy, which means you're literally mapping the same area and the same location. And there is a small backpack which you have to carry with yourself, and then that connects with a base station. So that's where all the data location correction takes place. And then you get the locations on the GPS. When you come back to your office, you can upload those GPS points onto a map. So they could be possibly locations where you wanted to sample. So all those samples will appear on a map. And this is a software which you use to download the GPS locations onto the GIS system. It's an interfacing software. And 2 sets of ground truth, because we were doing 2 types of classification. One is by the more traditional supervised classification. I'll explain what these 2 are in a few minutes from now. And then the other one is object-based classification. So that's how the image looks like. This is the panchromatic image. Now, when it came to field work and sampling, we used a panchromatic image simply because the resolution is 1 meter by 1 meter. And we can see those features very clearly. And after we did them, there are actually some points out here which you can't see. There are actually some yellow lines which for some reason are not appearing on the screen. But I do have a paper. You can obviously go and link to those papers, and you can see better images. But this image, actually, we collected a lot of points, and we marked those points by using GIS polygons. So for instance, we are interested in this white roof building. We literally marked this white roof building and also found out the area of that roof. So like that, we collected samples all across the image. The purpose of collecting these samples was to cross-check and verify the classification results later on. So in digital image classification, basically, it's the automated grouping of all or selected land cover features into summary categories. So you can have as many categories like residential land use. You can say recreational sites. You can say wetlands. So you might have different types of land use classes. So in supervised classification, you basically accumulate all the pixels which belong to a certain category. So if you're saying water bodies, all the pixels will have the same digital numbers, which reflect a water body. So that's how you group all these pixels on the image. And that's what your map will look like in the end. So that's the supervised method where you actually train the pixel. You tell the pixel that this is a water body, and then you run a classification. You have to have that prior knowledge before. So that's why it's called supervised classification. You're supervising the process. And then the other classification is what the entire world is actually moving to, because after a certain level, you cannot get more accuracies. So you have to use an object-based approach. In an object-based approach, we use the size of an object, we use the texture of an object, we use the pattern of an object, we use the association of features, we used a lot of variables. For example, if there are two buildings which have similar types of roofs, terracotta roof, for example, they will look similar because the material is the same. But one roof may be a large commercial complex, and then the other one could be just a residential building. So how do you tell between these two? So basically, in an object-based approach, you look at the parking bays, the size, and then you distinguish between these two features. So you can build all that logic into the software. What's the size of this commercial establishment? A residential area is normally 50 by 100 square feet or something like that. And you can feed that information into the computer. So it actually separates the residential building from a commercial building. That's what we call it object-based. So we use scientific elements of visualization like shape, size. So this is what a computer does. That's the image. The top portion of the image is basically rocks. And the middle portion around here is agricultural areas. And A is a water body, as you can see here. And this is when you look at the image on a computer, it has different pixels. And you can see that this portion of the image is the same as this portion of the image. And this is basically C, which is corresponding to rocks. So finally, when you do the classification, you're grouping all these pixels on an image. And these are the different bands. Maybe this sensor has 3 bands. That's why they're showing you 1, 2, and 3 bands. And the pixel alignment is always the same, to answer the question by this professor. They're all aligned because they're all referenced to the same location. And once you classify them, then you get this digital GIS map. So from a remote sensing data, you can analyze a remote sensing data. You can classify it depending on your classification and your interest. And finally, you can come up with a map like this, which can be used for different purposes. So I won't go through this. This is the per pixel method. And the spectral value of a specific pixel were assigned to one of the class features. I did mention in the beginning that a water body will have a spectral signature which is different from a tree, because the molecular composition and the size and all the atom structure is different. So it reflects differently. Some classes were spectrally similar. For instance, if you're trying to map a concrete building from a road, they might look similar because spectrally they are both highly reflecting objects. So there is a case for you to separate it by using some other methods. So there are some limitations in remote sensing, which a lot of scientists are trying to find a way out. And one way is to go the object-based technology approach, where you look at the shape and the size and the association and the pattern and so on. So object-based classification is basically a new method, which I've already explained. So I'll quickly skip this slide. We use tone, shape, size, pattern, texture, shadow, association. Some instances, we use the shadow to measure the height of buildings. That's the geometric engineering. That's what we actually do. But that's only for those projects where people are really interested in looking at the buildings. It's not something which you can do for the entire image. So again, I would skip this. This is a little technical. We use membership functions to find out a specific object. We use these types of different functions here. I suppose I'll skip this because it's a bit too technical here. And we use different types of membership functions to define what is an object on a map. So just to summarize, before I show you some graphics of the output which we got over New York City, we have both spectral, you understand spectral now, and spatial attributes. Then we have spectral values, which were computed based on reflectance and absorption footprints of each feature. Then we have spatial attributes were computed based on elements of scientific visualization. So we combined these two approaches to create a map over New York City. When I said New York City, I'm covering all the 5 boroughs at a given point in time. And the model I develop can be applied to the same area, same image at any point in time. So if you want to map the changes, apply the same algorithm to an image taken in 2000, and then subtract, do an image subtraction. So it'll tell you how many places have new trees, how many places have actually been urbanized since then. And these are some of the findings of this study. We came up with all these algorithms and relationships. This is the 10th September image taken out in 2003. This is the 2004 image, January 2008. And these are some of the features which we generated by using these algorithms. So that's how the image, that's how the map of certain area of New York City, as you can see here. Sorry. So if you don't mind, I'd like to turn off some more lights so that you can see it clearly. As you can see here, this is a vacant grassy area. And you see small yellow dots here. They're actually trees. So what I'm trying to show you here in this patch of land here is we've been able to map respective trees and the shadows also, and also the green areas. And this obviously, this is the map which we created. It's not the way the data was given to us. So this is a GIS layer which we created on top of this map. And this is the water body, as you can see very clearly by the pattern. And these little small green areas which you see between houses are trees. They are independent tree crowns embedded in residential areas. I say residential because it conforms to the size of a normal residential roof here. And the pattern kind of gives it away. And these are the open spaces. So we were able to map out trees, water bodies, vegetation, even shadow. Dark roof, we were able to map out 3 different types of roofs: dark roof, white roof, and gray roof. So please don't be limited by what's done in this study. My focus was to generate these classes. For your set of interests, you might have a different focus altogether. But you can still get the same effective results. Now this was using a supervised classification. When we did the accuracy assessment, it was close to about 75%. Which is normally accepted in remote sensing fraternity. But we wanted to go a step further. So we tried the object-oriented method.
I think there's a question.
Yeah, sorry. Yeah.
I'll hold my question too.
All right, no worries. So here, so object-oriented, we used that, and we lifted the accuracy to about 82%. So it went up from 75 to 82. So we found that this object-oriented method, although it has some limitations, it works well, better than the supervised classification, which simply means, in simple language, all the features cannot be spectrally resolved. You have to sometimes use spectral information along with scientific elements of visualization, like the size, shape, pattern, to be able to separate it. So coming to the close of my presentation. So in conclusion, we analyzed time series of, when I say time series, we did this for a whole lot of images from 2000 to 2010 over New York City. And this study appears on the company's website, on GOI website. If anyone's interested, I can show you the link. It gives out some more details. We developed spectral and spatial attributes to extract vegetation features. We tested the model on other images, same resolution, same characteristics, to understand whether this algorithm will work well on the other images. 2 undergraduates were trained. I made a special request to Yehuda Klein, who's the Earth and Environmental Studies Executive Officer, and he was kind enough to give me space in the graduate center. So that's a very attractive place for youngsters. So I thought, I could get them over there, and they put in a lot of work. So there were 2 of them who were studying for a medical program, but they were interested in remote sensing, so I kind of spent a lot of time, trained them, and got them to do this. We improved the classification accuracy by using an object-based method, and the results of this project are on that link, which I can again make it available to you at any time you wanted to contact me. I wanted to thank PSC, CUNY, and GOI for funding the study, and also thanks to the Provost for giving me the opportunity, and the team of reviewers who actually assessed the application. And many thanks to Linda and Holger to actually make all this possible. So thank you very much for your attention. If you have any questions, I'm sorry.